Hi guys, Chapter 16, Heat Transfer, is what we're going to be discussing. Now we talked last chapter about the fact that heat can transfer, right? It moves from hot to cold, right? Well, in this chapter we're going to delve into that a little bit more because there's three processes by which heat can transfer: conduction, convection, and radiation. All right? We're going to start with conduction. Alright, conduction can transfer by molecular collisions within a substance. So take a look at the picture here. Now you put the end of this metal poker in the fire. That fire definitely transfers some heat to the metal here. Well, what are those molecules at the end of that stick going to do? Well, they're going to start getting all excited and moving and colliding more, and then they hit their neighbor in a collision, transfer a little bit of that energy. It hits its neighbor and so on and so forth until after a bit, you've got the heat has traveled all the way up to where your hand is, and ouch, you get a little burn. That's conduction. Right? The heat is conducted from one molecule to the next through collision. Okay? Now, depending on the type of material you have will depend on how well it can conduct. Right? You need loose electrons that are free to move around to conduct that energy. Right? Metals are really good conductors. Silver especially, copper, gold, all of those, good conductors. Poor conductors are molecules that have really tightly bound electrons. They're not free to move so much. They just kind of vibrate and jiggle in place. So they still transfer energy, but at a much slower rate. Right? Well, we call these poor conductors an insulator. Right? Good insulators are glass, wood, wool, right? Any substance that can trap air, right? Like fur on animals, that's how they stay warm. Their fur traps the air, right? That is a good insulator, right? Because it's trapping that air in there. That air stays warm. Your body heat keeps it warm. You know, like you've got one of those big puffy winter coats, right? All that air is getting trapped in there, then your body heat keeps it warm. And that insulates you from the cold, doesn't allow your heat to escape. Alright, so a little bit more about insulators. Alright, they do not prevent the flow of energy, they just slow it down. Alright, insulation, this fiberglass insulation, pink stuff in the walls of your house, right? That's what keeps your heat in the house in the winter and keeps the heat out of your house in the summer. Alright? Walking barefoot across hot coals. What does this have to do with anything? Well, how can you do that and not get your feet burned up? Alright? Well, you have a lot of moisture in your skin, right? Which helps your skin, of course, stay healthy and strong, but it also makes it not a great conductor. Now, your body, of course, can still conduct energy, right? But if you've got wet feet, really moist feet, all right, it's not going to conduct that well. And so you can walk really fast across those hot coals and not have any horrible burns. All right, convection. Second process we're going to talk about is the transfer of bulk flow. All right, transfer of energy through bulk flow. All right, well, to have a flow, you've got to have a fluid, meaning a liquid or a gas. Right? In the picture here, we're talking about air, right? Our gas. So we have this heater coil, a radiator right here. Right? It heats up all the air surrounding it. Right? Warm air rises. You've probably heard that. Right? It rises because those molecules start getting all that energy and expanding, having all these collisions, and so the volume of that gas gets bigger, which means it's less dense, so it'll rise. Right? Well, when that air rises up, look what happens. The cold air rushes in to take its place, and then what do you have? You get this flow going. All right? That's convection. Okay? Here's another example of convection. All right? Winds off a shore, right? Because of the different heat capacities of water versus land, right? Will change how the flow of air goes. Radiation, our third process. Right? Radiation is the transfer of energy from the sun through empty space. Now what does empty space mean? Well, it's a void, it's a vacuum, there's absolutely nothing there. Alright? This is how the sun heats the earth. Alright? Now it's different from conduction and convection because it doesn't need a medium to travel through. Right? Like with conduction we had that iron poker. With convection we talked about air. Well, in outer space there's nothing out there, no air, nothing. Right? Radiation's special in that way because it doesn't need anything to travel through. Right? Now radiant energy or radiation does not mean, ooh, the scary stuff. Right? Radiation just means light. Right? And there are many different types of light, many different energies of light, from the scary radiation to just sunlight or flipping on the light in the house, right? Or a radio wave, a microwave. All those are types of radiation. All right? Now, how much energy it carries and how long or short that light wave is, will depend on what type you have, right? And I've got some charts here to help you with that. All right, so if we have low frequency, right? Low frequency means that it's going slow. Look at this first picture down here. Nice and slow and a long wave, right? Well, high frequency means a lot of energy. Boom, 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 right? That's this picture right here. See all these waves? So these are short waves, right? A wavelength is from one crest to another crest, right? So this wavelength is a lot shorter than this crest to this crest, right? All right. Well, this frequency can be related to our temperature, right? So look at this chart over here. The faster the frequency means more energy. More energy means what? Higher temp. Alright? Alright, so radiation. Emission and absorption. Alright? Every object emits radiation. Alright? We do. Everything on my desk does. The sun does. Everything emits radiation. Right? Whether it's absorbing light from the sun or reflecting light. Alright? So when the earth reflects light, we call that terrestrial radiation. Terrestrial meaning earth, right? Okay, now absorption of energy, right, can change depending on what type of material you have, what color the material is. Now, if something is a good absorber, right, then it's also going to be a good emitter. You can't have it one without the other, right? Because if that material is really conductive, it's a good conductor, that means it's going to take the heat in just as fast as it's going to give it off. Okay? Now reflection. That happens a lot with light. Okay? You ever wondered why when you drive by a house the windows look dark even in the daytime? Alright? Well, the sun's light goes in the windows, but then look what it does. It bounces around and reflects on all the surfaces. Some surfaces even absorb a little bit more than others, and so then by the time it bounces back to the window, there's very little that's going to come out to let you see what's in there, right? That's why the windows look dark, right? Dark colors absorb radiant energy more than light colors. Light colors reflect more, all right? Now Newton's law of cooling, all right? Newton's law of cooling says that how fast something cools depends on the temperature difference, all right? So let's say mom's cooking for Sunday dinner. She takes her hot pie out of the oven. Right? Where is it going to cool faster? In the freezer or on the table? Right? It's going to cool off faster in the freezer because of that big difference in the temperature. Alright? That's all Newton's law of cooling is telling you. Greenhouse effect. Alright, what happens with the greenhouse effect? Well, you have these high energy, short wavelength waves coming in from the sun. Comes through the glass on the greenhouse or in your car in the summer, for example. You have all these reflections bouncing around. Maybe the little plant absorbs some. Maybe the seats in your car absorb some. Right? So then that means some of this energy is getting transferred to the seats, to the flower, or losing it in collisions of reflection. Alright, so then you've got this longer wavelength, which now gets trapped, it can't pass back through the glass. So all that heat is stuck in the greenhouse, which is good for the plants, but if all that heat gets stuck in your car, whoo, not good. Alright? So here's what's happening with the car, right? The sun's rays go in, it bounces around, then it's a long wavelength, and now it just don't have the energy to get right back out through that glass, right? All the heat's trapped in your car. Alright, solar power, just a little piece of trivia. Alright, more energy from the sun hits the earth in 1 hour than all of the energy consumed by humans in an entire year. Just imagine if we could truly harness the energy of the sun. We could do amazing things. Alright, well that's chapter 16, guys. Make sure you read your chapter. Call me, email me, message me if you have any questions. Alright, and I will talk to you later.